Okay, so thank you all for coming. Welcome to our monthly Canvas Talks, which highlight the fantastic research being carried out by postdoctoral fellows in Canada. Postdocs in Canada produce a huge fraction of astronomy's published papers while they're precariously employed in temporary positions. So this talk series is to highlight some of that impressive work. I'm Samantha Lawler. I am here on the Treaty 4 territory, hosting this talk series. This is the land of the Nahiawuk, Anishinaabeg, Dakota, Lakota, Nakota, and the homeland of the Métis-Michif. Today's speaker is Jane Kaczmarek. She is a postdoctoral fellow at the Dominion Radio Astrophysical Observatory, which is on the traditional, ancestral, unceded territory of the Salish Okanagan people. She completed her PhD at the University of Sydney, followed by work on the Parkes Radio Telescope. She's currently working on an Outrigger station for the CHIME telescope to better understand fast radio bursts. So thank you so much for agreeing to give this talk today, and I will hand it over to Jane.
Thanks, Samantha. Thanks for the introduction. And thanks to everyone for tuning in. Some of you have heard me speak on this topic before, but today I'm going to focus actually more on some of the challenges of the CHIME Outrigger project and show you some of our recent successes over those. So there we go. So the outline is as follows. I mean, you can't give an FRB talk about it, at least without describing what an FRB is for the few of us that blissfully don't know. And then we'll talk about why CHIME, who has dominated the FRB space for so long, seeks to do better and how we're going to do that through the CHIME Outriggers, excuse me, and then into the challenges and the way that we've overcome them. So CHIME and CHIME FRB is a behemoth of collaborations and collaborators. So the work that I'll be presenting here is not just my own, but actually from an army of people from these institutions and many, many more. So straight into FRBs, what is in a name, you may ask? Well, the name tries to say it all. Fast radio bursts are the fastest transient events in the radio sky, lasting for a couple microseconds to a few milliseconds. And they are bright. When I say bright, I mean they are typically as bright as a radio galaxy that are only lasting this fraction of a second. So there is something very interesting going on with the physics to be able to create that type of light on that type of time scale. We do know that they are extragalactic. We can tell that from something called a dispersion measure, which is actually the interaction of the radio light with the cold dispersed plasma in between us and the emitting whatever it is. We'll talk about that in a little bit. And they are prolific. I mean, we have more than 1,000 FRBs happening in the sky a year, and we're really only able to capture a fraction of those. And of the many, many events that are happening, most of them don't repeat. They are a one-off kind of burst event. About 10% actually we now can say with what CHIME has seen do actually repeat. And we'll get to that as well. First FRB is actually shown on the plot on the right. It's also lovingly called the Lorimer burst. I remember learning about it in my first real astronomy course. And nobody believed it. And isn't it funny that this many years later, here I am giving my nth talk about FRBs, and it was detected with the Parkes Radio Telescope, a telescope that is near and dear to my heart. So I did say that we know that FRBs are extragalactic because of this dispersion measure, this interaction with cold plasma. If we're actually able to measure the total electron column density between us and the emitting mechanism or the progenitor, and we can do that because of the way that light interacts with the plasma itself, with lower frequencies actually being dispersed to a later time than the higher frequencies. So there's a time sweep associated with these events. Even though we often just see them as a de-dispersed or a single pulse, there is a sweep across time. And so we can use that to estimate the total column density, apply some model, and put a distance to that, or a redshift. And so we know the closest ones have been quite close to our galaxy, but how far do they go? that question has not been answered, but this is trying to already hint at the fact that FRBs can be cosmological tools because they are all over the sky and all over in terms of redshift space. So CHIME was actually originally just designed to study the expansion rate of the universe by looking at the distribution of hydrogen at distant redshifts. But then wouldn't it just be a different story that we're telling if we didn't also add a dedicated FRB or transient backend to CHIME? So CHIME is at the Dominion Radio Astrophysical Observatory in Caledon, BC. One of the wonderful things about it is it's able to survey the entire northern sky every day. So it is has no moving parts, and we allow just for synthesis or the sky rotation to, I should say Earth rotation, to actually do our kind of synthesis imaging. We do observe contiguously from 400 to 800 megahertz. And in the case of CHIME, there are 4 100-meter cylinders that make up the entire phased array. So what does the sky look like to CHIME? Well, here it is. What you're seeing is the rotation of the sky and how CHIME can map the sky over the course of, and this is probably a few days worth of integrated data. But that red bar in the middle is the primary beam. And so the primary beam is determined by the shape of the cylinder. And what is so unique to CHIME is that since it is a phased array, it has 4 cylinders, and within each of those cylinders, there's 256 dual polarization feeds. We can actually do beam forming through within that primary beam to be able to get to about, well, in the case of CHIME, to about, let's say ½ a degree, maybe a little better resolution. But with CHIME FRB, we can get to about an arc minute localization within that primary beam. With this type of survey strategy, CHIME has been able to detect more than 10 times the FRBs than all other known FRBs before CHIME. And what does that look like in numbers? This is why CHIME has been so transformative in this space. So the plot here is, the first FRB I said was the Lorimer burst, and it said it was 2007, but actually it was archival data from Parkes. That was from 2001. So there was our first couple FRBs. Nobody was sure what was going on. Maybe it was a Parkes glitch, because gosh knows Parkes has plenty of those. But then other telescopes started seeing them. And so we go fast forward to almost 2 decades, and we've seen close to 50, still less than 100. CHIME turns on in 2018. CHIME FRB turns on in 2018, and this is the same scale. Well, this is the same numbers. The other ones are still plotted there, but you can't see it. It really is a new game with CHIME FRB. So we're getting about 2 to 3 detections of FRBs per day. The first catalog of the first 500 events is actually now public. And what does that look like? I did say earlier that FRBs happen anywhere on the sky, and well, here's the proof. These are those first 500 events and their localization or their distribution on the night sky or day sky, radio sky. There we go. The little triangles are the repeaters, so the ones that we've seen bursts from more than once. And you can see that the vast majority are only seen to happen once. And what do they look like in terms of frequency space or their spectra? They come in all different flavors, really. Some are broadband, some are narrowband, some have this kind of beating pattern. You have these sad trombone effects. They're all over the place. But if you want to see them all, check out the catalog. It's online. You can look at these types of waterfall plots for every single one of our events that have been published. So CHIME has been busy. Just in the last few years, we've been having multiple Nature papers that are really changing how we understand FRBs and how we can use them as cosmological tools. So we're already seeing that this is a very, very fast moving area of research, and CHIME has definitely been leading the way with some of that. So why study them though? I know we've talked about we don't know what they are and they're all over the place, but what can they really be used for? And that I've mentioned before, the potential to be cosmological tools. Well, we know that they are all over the universe or all over the sky, as I've shown in the previous plots. And we know we have rough estimates of their distances because we have measured dispersion measures. And so we know that they are distributed throughout the universe, and they pass through large fractions of the universe, large path lengths at the very least. So we're able to actually get snapshots of the universe's evolution from these FRB flashes. And as part of that, we're able to measure an otherwise unprobable part of the universe, the cold, diffuse intergalactic medium, where otherwise we don't have ways of really being able to measure these types of things. And from that, you can, extrapolate to all the FRBs everywhere, and you get this large picture of what the large scale structure might start to look like at different redshifts. There's lots and lots of other ways that you can use it. You can actually start potentially measuring cosmic magnetic fields with that. Not potentially, you can measure cosmic magnetic fields with FRBs. You can start looking for lensed FRBs and looking for complex and compact systems. And there's lots of things you can start to study, galaxy halos, et cetera, et cetera, et cetera. But there's something that all of this relies on. Well, at least the future application is going to heavily rely on, and that is localization. Yes, we have a rough estimate of redshift with dispersion measure, but dispersion measure is kind of hand wavy when it comes to distances because there's lots of potentially intervening things. You also, of the all of the hundreds of FRBs that have been detected, only a handful have actually been localized to their host galaxy. Host galaxy localization is really important because it gives us that redshift and it allows us to actually start to study the environment of the FRB to be able to account for any environmental variables, start studying what the progenitor might be, et cetera, et cetera. But in order to do it, we need about an arc-second localization in order to get just to association with the galaxy. And again, CHIME is about, well, an arc-minute, so 60 times worse. There's still really no understanding of what the environment or even the galaxy population is of these FRB hosts. So there's a lot of questions that still exist. And then these questions are crucial to us being able to use FRBs further to study the universe. Right, so I said that CHIME FRB has a detection radius of, a localization radius of about an arc-minute. Well, here is the Hubble Extreme Deep Field, about 2 arc-minutes, where you can see every single one of those as a galaxy. So there's really no chance that CHIME is going to be able to nail this down to specific galaxies if you're talking especially about high redshift FRBs. Another way of demonstrating this fact is low angular resolution. Got that arc on the left. This is the CHIME localization of an FRB, where every one of those pink squares is a known catalog position of a galaxy. This particular event, this particular FRB event was a repeater, so we were able to look at it with the EVN, and we got to milliarc second localization to this galaxy, not even just to the spiral arm, but to a dust cloud that where this FRB had originated from. So we can start with better localization and precise localization at that. You can actually start to get down to the environmental impacts or the environmental variables that can lead to FRBs. Okay, right. This is a very, very intro to interferometry, because how do you get better localization or better resolution? Well, you got to go to interferometry, right? So the point of interferometry is just to put multiple dishes. CHIME is an interferometer, just with an almost zero spacing, because the cylinders are touching and they're only separated by a max of 60 meters. But really the importance here is being able to use multiple dishes at some distance to be able to get a coherent and constructive signal from some radio signal far, far away. But what we want to do with CHIME to get that type of, let's look into this dust cloud where this FRB came from. In order to do that, we need to go further than just interferometry, and we have to go into the world of VLBI, so very long baseline interferometry, where now we're talking about physically separated systems that need to work constructively. And so it's difficult for a few reasons. Just traditionally, it's difficult because you have different systems, different clocks, different cable lengths, different temperatures, different ionosphere, blah, 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 the list goes on, to be able to measure that delay, the arrival time delay of each wave from some distant radio source. And that's kind of what I'm summarizing at the bottom there, is that there's a lot of things that need to be well understood in order to in order to be able to correlate your data constructively. Now, we're going to do it. We decided, you know what, this is what CHIME needs to do in order to get this type of resolution that we want. And what is that resolution that we're aiming for? 50 milliarc seconds. So our goal, the CHIME Outriggers, which is a dedicated VLBI network of CHIME-like cylinders and CHIME-like antennas, is going to try and localize over 1,000 FRBs to 50 milliarc second precision in 2 years. And we can get to that 50 milliarc second target by having really long baselines. The longest baseline will be formed between CHIME at DRAO and Green Bank Radio Observatory, where there will be a single cylinder at the observatory there. And we have a couple other, well, there will be 3 stations. We currently know of 2. The other is what we're calling our local Outrigger at Allenby, or it's actually part of close to Princeton, BC. And I'll talk about that in a little bit. So, but why 50 milliarc seconds? At 50 milliarc seconds, we easily get the host galaxy identification. We also are able to determine the location within that host. Start looking at the dust cloud, start looking at the spiral arm, start looking at the halo if you want. And we can measure the distance because we'll be able to cross-correlate with optical surveys to get redshifts. Not even optical surveys, sometimes we'll have to do pointed observations to get redshift, but that is something that is planned. So what about the Outriggers themselves? I did say the longest baseline will be formed between CHIME and another Outrigger at GBO. And the shortest baseline will be only 85 kilometers, which will give us about an arc second resolution from just that one baseline. Or that one arc second, I should say it was 1D arc second. So they will be CHIME-like cylinders. And also importantly, they're going to all be rotated, tilted, and rolled to share the same, to be staring at the same sky as CHIME. So while we're talking about big distances, these things are going, in the case of the figure I've shown here, is the cylinder that will be at GBO. One edge will be raised 12 meters up to make sure that it's seeing the same sky. We are prioritizing trying to put our cylinders at existing observatories because, as we are learning with the case of Allenby, and everyone probably already knows, green sites are a lot of work and a lot of time. And something I mentioned, but I want to stress again, is that the Outriggers are going to be a dedicated VLBI survey system. VLBI surveys, there aren't really many of them, if there are any at all. So this is going to be unique in its own right to be constantly doing VLBI over large swaths of the sky. So timeline, where are we? Well, we are right here, and I'm going to prove to you that we are actually at that. In fact, we're a little ahead of schedule with GBO. So we are expecting first light for Allenby at the end of this year, with the Green Bank cylinder coming online shortly thereafter. Green Bank, one of the reasons that we like it as well, rather than just being a dedicated observatory, it is a radio quiet zone, so we don't lose any of the bandwidth or frequency space due to interference. And it will just be a single cylinder rather than the 4 that we have at CHIME, but 20 by 64 meters. And we've also broken ground. So you might see in this beautiful patch of green, which is very rare to see, at least in BC right now, that little white hut there is our RF room. So that will hold all of the computer and mechanics and everything that we will need to actually operate the system. And ground has been broken. This picture is from yesterday. They are putting in roads into where our cylinder will be placed. So it is happening at GBO. Now, Allenby, something that I spend a lot of my time thinking about, is what we're calling our local Outrigger. It's only 85 kilometer baseline with CHIME, but about 120 kilometer drive from DRAO. And we call it local because it takes about a little over an hour to get there. So it's kind of where we were cutting our teeth, where we are going to be cutting our teeth with the Outrigger project. It is a VLBI system because they are completely physically separate. And we're in the process of building local project knowledge so that it gets community support behind it. And it'll be a little bit smaller than GBO, purely because it's very hard, and I did not appreciate this until I moved here. It's very hard to find flat land in BC that is not dedicated to agricultural use. So the history of Allenby does actually play a part in why we've picked this site. It used to be a mine. And so that picture on the top is actually the old site that now looks like this and is covered in cow, well, let's just say cows left us presents. We now have a fence, so what's there will be there for a while. And another reason we picked Allenby is, no, it's not a dedicated radio quiet zone like GBO is, but if you look at the spectrum here, which is yellow for Allenby and kind of darker, kind of hard to see goldenrod is CHIME, we don't lose any additional frequency space at Allenby compared to CHIME. So LT is absolutely booming. I have a better signal there than I do in my house in Summerland, but that's already gone because CHIME already has lost that. So that's another really good thing to notice, that we haven't lost anything even without the radio protection. Another thing I think is important to stress about Allenby of, yes, it's good to have a system to learn with, but it's not just that, it's so much more. With 1 arcsecond, which is formed by the 85 kilometer baseline, we can do 1D localizations to host galaxies. And so all of a sudden, a lot of those cosmological questions that we want to answer, like getting accurate redshifts and understanding host progenitor populations, we can do that with a single baseline in the middle of an old cow field. And in the case of the work by ASCAP, they were able to measure omega DM from just, omega baryon from just a handful of galaxies with ASCAP. And we'll be able to do that. If we're getting 2 to 3 events a day, we'll be able to do that, or at least constrain that plot there much better with just Allenby. So it is worth saying, and I will die on this hill, DRAO and Allenby, the baseline form between the two will be equivalent or better than all other FRB hunting telescopes, because we'll be a dedicated FRB hunting telescope. We have very broad band, and we have and we're low frequency, which is where we're getting a lot of the interesting FRB morphologies, and we'll be more sensitive than ASCAP as well. So what does Allenby look like now? Well, it no longer has cows. It has a beautiful CCAN as well that you can see, and it has our foundations already in the ground. Within that CCAN, we do have our RF room already installed and powered. And in that RF room, we have, well, in the RF room will go 2 of these beautiful computers, and I'll explain what they will do in just a little bit. So we do have all of the parts in hand. The computers are still at their test beds in Toronto, with plans to ship out soon. Okay, so the challenges. If low frequency FRB VLBI was easy, I wouldn't need to be so excited about this project because it would have been done already. But let's talk about how we are learning to do what needs to be done. So we do have prototypes. So the CHIME Pathfinder was actually the precursor to CHIME, where CHIME, we kind of, learned the ropes of CHIME and low frequency and non-moving phased arrays. And it actually has about a 400 meter baseline with CHIME. And we've been using that to learn some of our, to get used to our training wheels and eventually take them off. There is also at the Algonquin Radio Observatory in Ontario, there is a 10 meter dish that we have completely rewired to be another dedicated FRB antenna. And then at GBO, there is an array of dishes, I think of 10 meter dishes, no, I think they're 6 meter dishes called Tone, that has also been doing similar and related work. So the differences between regular VLBI and VLBI with Outriggers is, I've said it a few times, CHIME has phased arrays. It's a phased array telescope, and this means we have extremely high data rates if we wanted to do VLBI 24/7. How are we going to manage that? And we have to do blind VLBI because we don't know where or when an FRB will happen. So how do you calibrate that system? And then you have the iossue that low frequencies, well, a lot of things have extended or complex structures at the 400 to 800 megahertz band. Furthermore, the ionosphere has a 1 frequency dependence. So the ionosphere can absolutely dominate some of the delays that we are seeing between our Outrigger stations. So how are we going to deal with this? Take them piece by piece. So challenge 1 is the high data rates. So CHIME itself, if we were to record just raw baseband, has 6.5 terabit per second raw baseband dumps. But what we're going to do is, and what we have been doing, what CHIME FRB does, is it has a baseband dump, it runs an FRB search algorithm, and then if it says, yes, this has FRB potential, that amount of data from the ring buffer, which I think is for 35 seconds, is saved. We're just adding on to that by saying, okay, if it says yes, that there is an FRB or potential for an FRB, turns out the Outriggers are doing the same thing and they're just constantly buffering. And so if they get the trigger that there is a potential FRB, they will save that data. And that's still baseband, so it's still quite a bit. So how can we reduce it? Well, we're able to make tide array or treat the data as a tide array, and we're able to make the data sizes quite manageable to, I think, 200 gigabytes per event. So large, but not absolutely unmanageable. And so again, the machines here have been specifically designed, actually there's gonna be 2 of them, are specifically designed to be able to handle these data rates. And so the solution to this is just do a triggered voltage recording instead of having a constant readout of the system. Does it work? Well, yes, it does. And this work has been done, was carried out by Calvin Lung at MIT. And he used the Pathfinder, again, that 400-meter baseline with CHIME, as a quasi VLBI system. And we're able to do that because the 2 clocks of the 2 systems are actually different. So CHIME sees an FRB, we turn the Pathfinder back on, and it says, okay, if CHIME sees an FRB, can it pass that trigger fast enough? Can we get a big enough memory buffer to be able to still constructively see an event? And what you see, that's the autocorrelation between the different poles of CHIME. But when we do cross correlation with Pathfinder, you can still see a similar frequency structure of this event. So yes, it is working. This work has been written up in Calvin's recent paper. And I think I got the year wrong, apologies. It's 2021, it was early this year that it was published. So that is working. All right, step 2, this is also a lot of Calvin's work. FRBs happen anywhere and everywhere, right? So how are we going to calibrate an all sky system and an all time system when you can't point your telescope? Well, normally what you would do, you turn your telescope on and you want to say, okay, let's calibrate everything just to see where we are, right? You look at some big bright source that shared field of view from between the 2 telescopes, and you set your system up to some 0. Well, what happens with an FRB, at least what Kelvin did here for this proof of concept, is with a raw baseband dump, and since CHIME has such a huge field of view and is phased arrays, within that all sky dump, there are multiple calibrators. So let's say an FRB goes off, bam, well, dump that data from the sky, there will be calibrators in that field of view. And you can actually use some of those calibrators as typical phase calibrators to re-calibrate the system on the timescales of FRBs. So this, our solution here would be simultaneous phase calibration. Maybe we can just, whenever an FRB goes off, there's a bright calibrator in the field of view, let's use it and cross-correlate and find fringes, which works. Now, it's worth saying here that this has all been done again on that 400-meter baseline. We're not talking about very long baselines yet. And so this is proof of concept again. So from the event that I previously showed where we were talking about triggered voltage recording, there was another FRB that went off where we had also tried this. And what you're seeing here are where the events, or at least the localization from CHIME FRB, are the crosses. And the black dots are where other NVSS known calibrators are. And the black line is showing where, which calibrator was used as a phase calibrator for these events. And we also did it for 2 pulsars, just as our own sanity check. And you can see that it works from the figures on the right. This technique works. It works better for some calibrators than others, and that's because of source structure, because of like local fluctuations, et cetera, et cetera. But it's something that is easily manageable with a handful of calibrators within the field of view. Now, I did allude to this earlier, that was on short baselines. What happens when we talk about long baselines, where a lot of these calibrators are going to be resolved out. Well, the situation might look more like this, that an FRB goes off, bam, within the field of view of your Outrigger and CHIME, and there will be some time between when the next known calibrator comes into your field of view. So we'll call this time or angular separation delta t, and how far can we push it? Well, the the Outriggers have been designed to be stable for about 1,000 seconds. So we'd be able to fringe fit and cross correlate for 1,000 seconds after its last calibration. And that's because we actually inject a timing signal as a correlator input from our timing standards, which are not all masers, which is worth noting. So this corresponds to about 4 degrees of sky rotation. So we have about a 4 degree on either side separation within the field of view of an FRB to be able to find a calibrator or something that will work. Now, has this been shown to work? We'll get back to that. What are those calibrators though? We've already talked about how when we go to low frequencies, typical calibrators are going to be resolved, or my perfect example is 1934 minus 6-8, which is the gold standard baseband calibrator and flux calibrator in the Southern Hemisphere. Well, if you point at this thing with VLBI, it all of a sudden becomes complex. So what do? We click the mouse more times, there we go. And furthermore, there's even no VLBI catalog to date at these frequencies. LOFAR has tried, it's found a few, and I know it's working on some, but LOFAR is also a very different frequency range. It's not perfect. They have some good starting points. But then we add the fact CHIME is non-steerable, so we actually need an all-sky VLBI network to be able to, VLBI calibrator network to be able to carry this out. So the question still remains, what are we going to use? And the question is, well, maybe answered with pulsars. Pulsars, we know, are compact objects. They are point-like. Yes, some will have winds, some are scattered, but those are types of things that you can actually deal with in the imaging domain. So what our approach to this is going to be is create an all-sky network of bright pulsars to serve as our phase calibrators. And that's what we're seeing on the picture on the right, is that is our distribution of 100 pulsars that we have actually targeted with VLBA to get ultra precise localizations of these things. Again, we need even better localizations than most pulsars. Yes, some pulsars you can get very accurate positions relative to the solar system barycenter through timing, but we want everything referenced to the ICRF, so the International Celestial Reference Frame, the unmoving quasars of the distant sky, right? So we've been able to do this for the observing just finished last week for these 100 pulsars. We will get 5 milli-arcsecond localization to each of these pulsars, and we will use those as our phase calibrators. So again, the whole goal of the Outriggers is to be able to localize FRBs to within 50 milli-arcseconds. So if we have a calibrator with an unknown position to 20 milli-arcseconds, that's a large chunk of our total error budget, including all the systematics and the ionosphere, which we haven't even dealt with yet. So getting our calibrators as well known as possible is crucial to being able to localize our FRBs. And this work will be, a large portion of this work is being carried out by Alice Curtin, who is a PhD student at McGill. Right, and so the yellow that you're seeing, I haven't even talked about that. The yellow that you're seeing is that 1,000 seconds. So that 4 degrees of sky rotation in either way from our clocking stability. So that little white strip that I'm pointing to with that arrow is about 30 minutes. So there's only 30 minutes out of 24 hours where we won't be reaching our localization standards. But even then we may, because there's some very interesting work being done by a team out of MIT that is showing that a strong likelihood of being able to project clocking stability forward to be able to actually elongate our timing standards. Right, so the ionosphere. I remember before I took this job, my previous colleagues were saying, well, there's no way that they'll be able to deal with the ionosphere. How are they going to do it? the ionosphere does dominate at these frequencies because of its 1 over frequency dependence. So you have these strong delay, a few nanosecond delay, unique to each site, just coming from the ionosphere. And yes, there are ionospheric models on what's going on above, all over at least in this image shows in North America, but they aren't accurate enough for us to be able to reach our localization goal. So there's a few things that we can do. But I want to also show that the ionospheric delay and the geometric delay, if you're looking at the likelihood contour, sorry, what's shown on the right is the likelihood contours of the ionospheric delay on the left and the geometric delay on the bottom. And this is real data for the localization of the Crab pulsar between CHIME and ARO, so the 10-meter dish out in Ontario. And you can see that there's a very large range of delays that we can't really narrow down. And delay is directly related to localization precision. So what are we going to do? How do we break this degeneracy? Well, it turns out that CHIME has a huge leg up because it is so broadband. So for very, very broadband events and very bright events, we will be able to, comparing the two plots on the right, the top plot is showing for 200 megahertz of bandwidth, so it's half of the CHIME band, and an event that's only signal to noise at 6.5, you see all of the likelihood wells that a particular event could live in. That's not telling us anything. But for a bright broadband event, the one on the bottom, which is a signal to noise of 65, there are very, very few. So we're able to get, to break this kind of, we can solve internally, I should say, for this relationship between the geometric delay and the ionospheric delay, just because we have so much frequency space to work with. But what happens in the case of the dim events? We just have to throw up our hands and say we'll never get them? Not quite. Again, Allenby comes to be very useful here because Allenby, with that 85-kilometer baseline with CHIME, often sits in the same cell of the ionosphere. So we have two samples of that within that path length or that delay, which doing a localization just between Allenby and CHIME will be like giving us a prior as to which well we are actually living in, which minima, which likelihood minima we are in to actually solve for the real delay. Now, has this been shown to work? Watch this space. So far, if we revisit the challenges and how we've overcome them, short baseline tests, we've been able to show that we can do triggered voltage recording, and we can show that blind VLBI and in-field calibration does work. Again, this work being summarized in Calvin's recent paper, and Calvin's smiling face shown there. This was all done with Pathfinder. Now, what about very long baselines? I haven't talked much about what we've done at GBO with tone, and I've only mentioned ARO a few times. So what do we do with the 3,000 kilometer or 8 mega lambda baselines? Well, we use the Crab pulsar because it's so darn bright, and a 10-meter dish can easily see a giant pulse from Crab. So Tomas Casanelli at University of Toronto has actually written up a successful cross-correlation and localization of the Crab pulsar with between ARO, 10-meter dish, and CHIME. And we are expecting a referee report shortly there. And then we've done the same with tone. And so Pranav Sanghavi has been able to do this with the array at GBO and been able to show a similar success. So what about putting them all together? We have 3 prototypes and CHIME. We have the baseline lengths that we want to get the angular resolution and the localization precision that we have sought from the beginning of the Outrigger project. Can we put them all together? Well, I can tell you this much. We can successfully cross-correlate ARO and tone. That has been done also between Tomas and Pranav with Crab pulsar. But what about something interesting? Watch this space, and I encourage you to attend FRB 2021 if you want to hear the latest and greatest from the Outrigger team It is unfortunately not my news to share. So I hope that was tempting. I hope it was enlightening, and I hope you are just as excited as we are at CHIME to get these things on the sky. In summary, FRBs are incredibly useful, not just because they are a big mystery, but because by understanding them, we're able to use them as better cosmological tools. The Outriggers are going to localize FRBs in order for us to be able to study their progenitors, their environments, and then apply that knowledge to being able to disentangle the complex sightlines that we're seeing. The VLBI that we're doing at this low frequency with the Outriggers is possible because we have an awesome team, and we have already shown that we can do trigger baseband recording to manage the huge data rates. We can use unique and novel calibration techniques to be able to keep the array in phase. And we are well and truly underway to, well, first light later this year. And so we have a demonstrated end-to-end over 3,000 kilometer baseline at CHIME frequencies for FRBs and pulsars. And now we just need to, well, wait for the steel to go up, which happens next week at Allenby, which is very exciting. So thank you very much. And I will take any questions.
Thank you. That was a fantastic talk. I learned so much. Since I'm chairing, I'm gonna ask you the first question. So all I think about recently is mega constellations, right? So there's going to be thousands, tens of thousands of these flying right over all your sites. How is that going to affect chimes? Or is it different frequencies? Is it, you don't know, you have to wait and see? How is that going?
I believe that they aren't too bad in our frequencies. Alex, I'm going to look to you to jump in if I am wrong. I don't know of any actually having gone over CHIME yet, but surely they have.
Yeah, my instinct is the same. I think they mostly transmit up in the gigahertz range.
Yeah.
So I don't think they're transmitters at our frequencies.
Our bigger issues are local, like ground-based. So people driving by with cell phones on and surprise new cell phone towers going up within direct line of sight to the telescope, which definitely didn't happen.
The CHIME band has gotten noticeably worse in the last few months as new towers have gone up.
So that's one of the reasons why the Allenby spectrum is fine, is because CHIME has lost a lot, and DRAO has lost a lot just in the last decade. But mega constellations, luckily, are not that bad. Airplanes, helicopters, that's a different story, but they're transient as well. And so fine, we lose a few seconds of data, right? Because while CHIME can see the quote unquote whole sky in a day, it's still a fairly skinny beam. So if we lose a few minutes of data a day due to something like that, it's not the end of the world, but something that sadly has to be faced by all.
Yeah, good to hear. Let's see, I see William Wall has his hand up. You know, unmute yourself and ask.
Yeah, hi. I'm interested in the sources that you're observing, the FRBs themselves. The reason they appear so bright is probably because they're not isotropic emitters, especially if they're magnetars. Is there anything in the data that can directly tell you something about how isotropic the emission is?
I think you would need to use mostly baseband data for that. And there are very few events for which we actually keep that much information. I'm also going to fully admit that I'm not the person to ask. If there is an answer, it would be probably in Ziggy's morphology paper. So Ziggy Planis has submitted it was accepted, FRB morphologies paper that went through the entire FRB catalog. And if there's an answer, it'll be in that paper. And I'm sorry, I can't answer more than that.
Thanks.
Sorry.
Any other questions? There was one question in the chat about the shape being different for the Outriggers, but I think that was answered.
Yeah, no, they will be the same. They will be the same, well, to whatever degree we can get them to as CHIME itself, and the rotation and yaw of each of the cylinders will be good to within 0.05 of a degree. So very, very overwhelming overlap between their fields of view.
Cool. Okay, any other questions from people watching? You can raise your hand or unmute yourself. Anybody? I'm going to ask one more question first. So you talked a lot about ionosphere issues. Is that going to become more problematic as we head into solar max? Or is all of the calibration that you talked about going to work just fine? Or you don't know yet?
You have mentioned something that we're trying not to think about, and we're just assuming it's going to be fine. We're not assuming it's going to be fine. We have no reason to think it won't be fine because our calibration doesn't rely on, it's not sensitive to the total electron content, we just need to be able to measure it. So very, very small scale fluctuations will be difficult. So when we're talking about things where Allenby and CHIME are in different ionosphere chunks, that will be difficult. But the fact that the ionosphere is changing quickly and dramatically and dynamically, we should be okay, but you can't test that until it actually happens.
Okay.
But yeah, we're going, we should be good, right? Yeah, it should be.
Sounds like a good plan to me, but I know nothing about this research. So William, you have another question?
Yeah, I might as well ask the question I put in chat. You talk about the ionosphere being a problem, but it seems it's also an opportunity because you could do research on the ionosphere itself, and there must be people interested in that. So what could you learn about the ionosphere? I guess timescales, the fluctuations and things like that.
Yeah, and LOFAR has done some amazing work on the time scale and angular scale of the ionosphere, at least at lower frequencies. So we could do something similar. The only gotcha will be that we have designed the Outriggers currently to just be able to transport enough data to cover our events per day, right? So we talk about the memory buffer just to be able to keep data, but also the amount of data that we can physically get off of site every day was designed for FRBs only. So this is something that could be done further down the road with moderate modifications, but nothing too crazy. But yes, we could, absolutely. And what I am personally very excited about is just creating a low frequency catalog of VLBI calibrators, because yeah, we're starting with pulsars, but we can still do in those baseband dumps the cross correlation to other known calibrators in the field of view. So all of a sudden, when we magically get the time, we will be able to start looking at these sources at these frequencies and at these baselines. So there's lots of other science that we can do that isn't just FRBs, but we have to remember that how we spec'd it was first just for the events themselves.
There'll be advances in technology, so you'll
do
it faster and so on.
Like the fact that this type of data processing can happen on just two essentially, well, two 2U computers is just epic. They're not normal computers, but still.
Cool. Any last questions from the audience? Oh, Vesna, go ahead and unmute yourself.
Hi. Sorry. Hi, everyone. I just wanted to thank you for this lecture, because I'm not in research. Since I'm in Canada, since I came here, I'm in teaching only, but I made a textbook, the first Canadian intro astronomy text. And in it, I have parks, of course. And in it also, I have CHIME in the newest edition. But the next edition is going to completely change the story with your interferometer. CHIME, first of all, we have a history of interferometry starting in Canada. And now I have a story linking fast radio bursts. And then, you see the section in chapter 4 about CHIME and interferometry and how it all started. And then Parkes, I had to put it there. That's by far my favorite radio telescope. And my department is laughing at me like they've never seen a person who has a favorite radio telescope. Oh. And Parkes is mine. And when I saw your biography, I said, oh my goodness.
That picture was taken from my old office. I used to live in Parkes. So it's
that is
and it's also something I didn't mention that I normally do is the first very long baseline interferometry experiment that was successful was between DRAO and ARO. So the fact that we're back there, yes, it's different telescopes this time, but it's amazing to actually watch how technology has changed just by comparing the two stories and the two times.
From 1960s to today, it's absolutely unbelievable. Thank you very much again. Thank you. I appreciate it.
I want to address Trey's question in the chat. Alex, you covered most of it, but in the case of Allenby, the reason Allenby is so small is because we literally couldn't find a larger parcel of land. Remembering the types of constraints that we have due to the orientation and the shared field of view, we could not find another flat piece of 80 meter, it was supposed to originally be 80 meters in BC within a reasonable drive of DRAO. So that's why we had to squish Allenby down. And if in kind of one of the pictures I showed, you can see there isn't much wiggle room between, if I can quickly go back here, where I'm standing, excuse me, to go like that. No, not working, whatever. Where I'm standing is at the fence post. So where, where this orange board is here will be the end lip. And then in the back, there's only another probably 6 meters. So that's really physically as big as we can fit in that site.
Okay, any final questions? We got a couple more minutes. If anybody has anything to ask. And if not, I think we are all done. And